The research put into artificial intelligence has been producing results rapidly. However, there's another area of active research that many people are starting to forget, and that is quantum computing. In this video, I'm going to be talking about quantum computation and quantum information theory. These two theories form the backbone for all of quantum computing. So let's begin without further ado. In order to comprehend quantum computation and quantum information, we must talk about the foundation for all of quantum computing, namely the qubit. So what is the difference between a qubit and a regular bit? And in order to understand that, we must talk about linear combinations and vectors. So let's begin by talking about the differences between a qubit and a bit. So over here we have the regular bit. This can either be a 0 or 1 position. But in a qubit, we can be in a superposition. Now you might be wondering, what is a superposition? To understand a more detailed view about superposition and some of the principles of quantum mechanics we will be using in this series, please do my videos on quantum mechanics. But right now, we're going to be just talking about superposition on a higher level, because we're going to be presuming that the person watching this already knows a lot about superposition. But to make this video pretty self-contained, let's talk about superposition itself. Superposition is just a combination of two states. Now, if you've heard of Schrodinger's cat, the cat can either be in one state or another if we're considering regular bits. But when we consider quantum mechanics, when we don't observe it, it's in both states at the same time, and that is the principle of superposition. Now, the combination of two states is pretty vague because it doesn't involve the mathematical part. There's something called the linear combination of two states, which is what we're going to be talking right now. So, the superposition we can represent as psi. Now, psi is usually representing the wave function in Schrodinger's equation, but right now we're going to be using it for superposition. So, a linear combination, LC, is just going to be psi is equal to A times the 0 vector plus B times the 1 vector. Now, in order to understand the transition from this equation to the algebraic form of a linear combination, we must understand the details behind the algebraic form. So, the algebraic form is just going to be AX plus BY is equivalent to C. We've all learned this in our Algebra 1 class, either in middle school or in high school, depending on when you learned it. But everyone knows that this is the standard form for a linear equation. Now, AX plus BY is equal to C can be mapped to this equation. So if we write it, we have A times the 0 vector equals B times the 1 vector, and this is going to be equivalent to psi. In other words, A and B are going to be the coefficients, and 0 and 1 are going to be the x's and y's in this equation, and psi is just going to be the superposition. So, labeling this equation, we have superposition, SP, and for this, we have vectors, starting from this point and then this point. Notice that 0 and 1 are going to be vectors. Now you might be wondering, why have we expressed vectors in such a weird and odd way? Notice that most of the time in quantum mechanics, we're not going to be using this form of vectors. We're just going to be writing 0 for just the 0 vector. But since we're doing it in a more specific and elaborate formation, we usually need these specific types of Dirac notation. In regular linear algebra, you probably might use 0 with an arrow on top, but this is Dirac notation. Now, I've made a whole video on Dirac notation, so please visit that if you want to understand the key necessity concepts behind Dirac notation itself. But in this video, we're just going to be presuming that the person watching this already has a great understanding of Dirac notation. But for those of you who don't, we're going to be explaining it right now. So, let's erase this description. So, Dirac notation. Now, the Dirac notation we're going to be talking about in this video is not all the details required in order to fully understand Dirac notation, but we're just going to be using it so that if you understand this part of Dirac notation, you'll understand the content in this video. So, Dirac notation is just a bracket. And I wrote bracket in a real weird way. This is just bra-ket. A bra is just represented as a vector like this. And a ket is just represented as a vector like this. So over here, these two vectors are called ket vectors. So we represent vectors like this. And that's pretty much all you need for Dirac notation in this video. Now we must understand the vector formation for 0 and 1. So what is the vector formation for 0 and 1 itself? This is a new concept that we haven't discussed in previous videos. The vector formation for 0 and the vector formation for 1 is just, for 0, it's 1, 0, and for 1, it's 0, 1. Notice that kets are expressed in column format and column vectors, whereas a bra is just represented in a row vector. So that's an important key detail that you must distinguish from when talking about bra and ket. Okay, so now that we've understood this, and we've understood the linear combination, let's now put it together to understand the main difference between the qubit and the bit. To be honest, the bit is more discrete. You have one value or you have the other value. You can't choose between any of the two values because that seems like a huge exaggeration. Before we had quantum computers, or the idea of quantum computers itself, it probably seemed like an exaggeration that you can involve quantum principles into digital computing principles and then create a whole new subject out of it, which is quantum computation and quantum information theory. So likewise, as you can see right here, the bits are discrete, whereas the qubits can allow for superposition. And superposition is expressed in linear combinations. And a linear combination just looks like this, where we represent the psi, usually used in the Schrodinger's wave function, as our superposition. Okay, before we continue the next part of this video, we have to thank the book Quantum Computation and Quantum Information by Michael A. Nielsen and Isaac L. Chuang. Okay, so let's continue with the video. Okay, so now we have logic gates for qubits. Now, this is going to be the end of this video. After we're going to be talking about this, we're going to end this video, but it's important to understand that there are much more logic gates than the ones we're going to be discussing. Now, you usually know about logic gates in regular computing. By the way, I'll probably make a history of quantum computation and quantum computing in another future video. And in the next video, by the way, we're going to be talking about even more detailed videos about logic gates, the block sphere, and etc. Now, the block sphere is a really cool thing because it has an advanced mechanism. And it's important to understand that the block sphere involves a lot of the principles that we talked about today. Okay, so let's continue. So for computing purposes, we have logic gates. We have the NOT gate, we have the OR gate, we have many more gates. Now, similarly, we're going to have these gates but in quantum computing. Now, quantum computation and quantum information theory is just a combination of three main disciplines, namely quantum mechanics, second, computer science, and third, information theory. When you combine these, you get quantum computation and quantum information theory. Notice that the previous video that we put is on matrix algebra. The reason we put it on matrix algebra is due to the fact that we're going to be using matrices in a lot of quantum computation and quantum information theory. Now, in order to understand how these work, we have to try to elaborate this and extend this, or more specifically, extrapolate this onto the 0 and 1 vectors. So let's write it in notation. X times a vector, or let's write it like this. X times the vector 1, 0 should equal what? Now, right now, I want you to try to find what this logic gate is going to be equivalent to. So what this logic gate is actually going to translate into a digital computer. Is it the NOT gate, is it the OR gate, or etc.? So in order to compute this, we must use matrix multiplication. So using this 2 by 2 matrix, we have 0, 1, 1, 0, and we're going to multiply it by 1, 0. In doing so, we get another column matrix. 0 times 1 is 0, plus 1 times 0 is 0. 1 times 1 is 1, plus 0 times 0 is 0, so hence we have 0 and 1. Now this just translates into the vector 1. And this, original, is just going to be the vector 0. So as you can see, this is indeed the NOT gate. Now, in the next video, and not about the history of quantum computation and quantum information, but more about the mathematics, we're going to be talking about block sphere, Pauli matrices, operators, and we're going to be talking about bases, linear independence. We're going to be talking about multiple more mathematical concepts. But it's important to understand that this helps form the foundation, and the NOT gate is also very important in quantum mechanics. So if you want to learn more about matrices and how to use matrices to solve equations and other things, then please visit my video on matrix solutions to system of linear equations, because I talk about that in detail. Okay, so let's continue. So as you can see, we've officially solved this, and we've solved this, and we've identified that this is a NOT gate, but in quantum computation and quantum information theory. So let's look at these two gates. Okay, so we have the Z gate. Now the Z gate doesn't have a specific name to it, but it's also we're just going to call it the Z gate. So what happens when we use it to the vector 0? So this, the Z, is just going to be 1, 0, 0, negative 1, all multiplied by 1, 0. We get 1 times 1 is 1, 0 times 0 is 0, so 1 plus 0. 0 times 1 is 0. Negative 1 times 0 is just going to be, obviously, 0. So we get 1, 0. So as you can see, this is kind of like the identity matrix in a sense. Now, the identity matrix is not this. The identity matrix, which is represented by I, is defined to be 1, 0, 0, and then 1. And we can use this to multiply anything. Now, when we use the identity matrix, it operates as a number 1. Because when we multiply to any specific type of vector, we're going to be getting that vector that we multiplied the identity matrix by. That's a special property of the identity matrix. Now, in this specific method over here, when we apply to Z-gate, we're just getting 1, 0. So it's kind of operating like the identity matrix in this one sense. Let's apply it to 0, 1 to see if we get 0, 1 as well. Well, we have 1 times 0 is 0. 0 times 1 is going to be 0. 0 times 0 is 0. Negative 1 times 1 is negative 1. Aha. We have a difference because 1 times 1 is 1. Well, 1 times 0 is 0. 0 times 1 is 0. And 0 times 0 is 0. Negative 1 times 1 is negative 1. So as you can see, we have this. And this is obviously different from this. Now you might be wondering, well, how is it different? Well, if you think about it, this is just a scalar, which we'll call lambda. Now the reason I'm using lambda for this is because in future videos when we talk about eigenvectors, eigenvalues, and other important things, we're going to be using lambda all the time. So let's multiply. Lambda times 0 and negative 0 and positive 1 has to equal to, obviously, 0 and negative 1. Well, obviously, we can deduce that lambda must be equivalent to negative 1, because when we multiply negative 1 to 0, we get 0, and negative 1 to 1 is just negative 1. Hence, we find that the lambda, or the scalar, is just negative 1. So, primarily, when we get the 1 vector, which is just this specifically, and apply the z gate, we're going to get the negative 1 vector. But when we apply 0, we're just going to get a positive 0, the same thing. So, this gate is kind of a unique gate. Now, let's go to our last gate that we're going to be talking about in this video. And this gate is much more complicated. It's called the Hadamard gate, and it's very useful in mathematics. So, let's apply. Let's apply 1 over the square root of 2 times 1 minus 1. We're going to multiply this with, let's say, 1 and 0. So let's first multiply these. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. Negative 1 times 0 is 0. So we got 1, 1. And we have to multiply 1 over the square root of 2. So this is going to be just the square root of 2, well, 1 over the square root of 2, and then 1 over the square root of 2. That's what we're going to be getting. Now, likewise, let's apply it to 0, 1. So we have 1 over the square root of 2 times 1, 1, 1, negative 1 times 0, 1. We're going to get 1 times 0 is 0, 1 times 1 is 1. So 1 times 1 is 0, negative 1 times 1 is negative 1. Aha, so we get this. And this will just be, because we have to multiply 1 over the square root of 2, to just be 1 over the square root of 2 times negative 1 over the square root of 2. Now, let's combine this. This is to be the 0 vector. And this is going to be, obviously, the 1 vector. So, if we do 0 plus 1, we're going to get 1 over square root of 2, and then 1 over square root of 2, plus 1 over square root of 2, negative 1 over square root of 2. That's what we'll get. So let's just check the last one. 1 times 0 is 0. 1 times 1 is 1. And 1 times 0 is 0. Negative 1 times 1 is negative 1. Okay. So now that we've talked about the Hadamard gate, we can make this video to an end. In the next video, we're going to be talking about Pauli matrices. We're going to be talking about operators, bases, linear dependence, and so on and so forth in future videos. We're also going to be talking about the eigenvalue problem, which is an eigenvector. So stay tuned to that. Now that we've talked about this, we can make this video to an end. If you like this video on quantum computation and quantum information theory, please like this button and subscribe, like the button and subscribe to this channel. Thank you.